Welcome, everyone, to another Explainer. Today, we're taking a seriously fascinating journey, starting straight from the dense, highly complex pages of a chemistry paper and bringing it right into the grounded, everyday reality of drug discovery. We are going to trace the entire life cycle of a newly synthesized molecule. We'll start from the exact moment it's conceived as a solution to a massive global problem and follow it all the way to its ultimate biological test in the lab. So if you love seeing how highly structured information actually translates into real-world science, well, you are definitely in the right place. Let's dive in.
Okay, so here's our roadmap for today. We're going to start with the rise of superbugs, followed by enter the Schiff bases, and then the chemical recipe. After that, we'll cover the molecular blueprint, hit the antibacterial tests, and finally wrap things up with the reality of research.
Section 1. The Rise of Superbugs, a Global Threat. Now, the stakes for this research, they absolutely couldn't be higher. Microbial infections are exponentially rising across the globe right now because of our own human activities and, the totally terrifying rise of drug-resistant superbugs. The everyday antibacterials we've relied on for decades, they are rapidly losing their effectiveness. It's a real problem. We are literally in a race against time to discover completely new therapeutics just to safeguard humanity. So, to fight this battle, chemists are turning to some very specific molecular structures. But before we get totally lost in the complex terminology of today's synthesis, let's define our chemical protagonist here, the Schiff base. Basically, it's a category of organic compounds made by condensing primary amines and aldehydes. Now, what you really need to remember here, the key takeaway is their defining feature, a stereochemistry that holds a nitrogen atom, totally locked in with a double bond. That double bond right there, it's the key to everything that follows.
Section 2. Enter the Schiff bases, the chemical candidates. Now you might be wondering, why are scientists looking at these specific molecules as our potential saviors in the medical field? Well, it all comes down to their sheer versatility. Schiff bases act as flexible chelation ligands, which basically means they can easily coordinate with numerous metals. Plus, they're highly stable and relatively easy to form. But most importantly for our story today, the highly unique properties of that imine group, specifically the electrophilic carbon atom and the nucleophilic nitrogen atom, allow them to actually interfere with specific enzyme functions in pathogens. This has led to proven antimicrobial, anti-inflammatory, and even anti-cancer effects in various studies. They are, quite literally, the ultimate biological building blocks.
Section 3. The Chemical Recipe, Cooking Up a Cure.
All right, let's look at exactly how researchers synthesized a brand new Schiff base. You can kind of think of lab synthesis like a highly precise, high-tech culinary recipe. The chemists kick things off by taking two raw ingredients, phenamyl and 1,2-diaminotoluene, and dissolving them in 70 milliliters of hot ethanol. Next, they gently refluxed or, boiled this mixture at exactly 60 degrees Celsius for 2 whole hours. And finally, they filtered and washed the product, isolating these brand new, beautiful, pale yellow needle crystals.
And this perfectly illustrates the chemical transformation. We have our raw ingredients, phenyl and 1,2-diaminotoluene. Through the sheer magic of that hot ethanol bath, and specifically the removal of two water molecules, they bond together to form our highly complex new challenger, 5-methyl 2,3-dithiopene-2-yal quinosanone. It's quite a mouthful, but what a transformation.
And guess what? The chemists were highly successful here. They actually achieved a 70% yield. Now, to put that into perspective, in the world of organic synthesis, hitting a 70% yield of a pure compound means you've executed an absolutely stellar, highly effective chemical cook.
Section 4. The Molecular Blueprint, Verifying the Suspect.
Okay, so they made it, but how do they actually know they made what they intended to make? Well, it's time for some chemical forensics. The physical architecture gives us our very first clue. The 3D crystal structure, which was captured via X-ray crystallography, reveals that the compound is entirely asymmetric, literally devoid of all symmetry elements. Meanwhile, its packing arrangement shows how intermolecular van der Waals forces act almost like microscopic Velcro, stabilizing these molecules and locking them into a neat, linear chain aligned right along the B-axis of the crystal.
Next up, researchers used an infrared, or IR, spectrum. Now, think of this like a molecular fingerprint. Different molecular bonds vibrate at completely different frequencies. The absolutely crucial indicator for us here is that sharp dip right at 1,580 inverse centimeters. That specific reading? That's the C=N bending vibration. It is the definitive, undeniable proof that the primary amine and the aldehyde successfully condensed, and our targeted imine linkage worked perfectly.
Just to be absolutely certain, they flashed a second fingerprint, the proton NMR spectrum.
This incredible tool actually maps out exactly where the hydrogen atoms are placed in the entire molecule. If you look closely at the data, there's a distinct peak right at 8 parts per million. That's the azimuthine peak, and it perfectly matches the theoretical atomic arrangement of the hydrogen atoms in our newly synthesized Schiff base. Boom! The verification is totally complete.
So to wrap up this whole verification phase, researchers needed to establish the compound's physical stability. With a molar refractivity of 91.05 cubic centimeters, a refractive index of 1.699, and a solid density of 1.307 grams per cubic centimeter, they decisively proved the compound is physically sound. It's completely stable all the way up to 140 degrees Celsius, and it is finally ready for biological testing.
Section 5. The antibacterial test. Into the Petri dish.
All right, here is where we shift from the pristine, perfectly controlled verification of the lab bench to the messy, high-stakes, real-world biological phase. The researchers utilized a classic in vitro agar-well diffusion test. They took a concentration of 300 micrograms per milliliter of our new pale yellow crystals, dissolved them up, and placed them into tiny little wells punched directly into an agar plate. And this plate was heavily seeded with dangerous, real-world bacterial pathogens, specifically Staphylococcus aureus and Salmonella typhi.
Now, to know if a drug is actually useful in the real world, it absolutely needs a benchmark, right? So they set up a direct head-to-head competition. The standard of care, doxycycline, going up against the challenger, our newly synthesized Schiff Base. They incubated these plates for 20 hours at a warm 37 degrees Celsius just to see which compound could inhibit bacterial growth the best.
Section 6. The reality of research. Biology is the judge.
So, we've seen a completely flawless chemical recipe and a totally perfect molecular verification, but here is the hard, unvarnished truth of scientific research. Despite that brilliant 70% synthesis yield, the perfectly aligned asymmetric crystal structure, and those flawless molecular fingerprints, the actual antibacterial activity of our new compound was pretty underwhelming. Compared to the powerful benchmark of doxycycline, our Schiff base exhibited only negligible to moderate activity against S. aureus and S. typhi. Now, the researchers did note that the solvent they used, DMSO, might have diluted the real effect slightly. But ultimately, the biological efficacy just didn't quite match up to the chemical perfection.
Which leaves us with this final, genuinely provocative thought. What does it actually mean for the future of medicine when perfectly synthesized, meticulously verified, and highly stable compounds still struggle to beat out existing drugs in the Petri dish? Well, it really underscores the immense, deeply humbling difficulty of modern drug discovery. A beautiful, perfect molecule on a slide doesn't always guarantee a miracle cure. It requires endless iteration, constant testing, and serious resilience. But you know what? That is exactly why scientists keep going back to the bench, because the very next Schiff base they synthesize just might be the one that changes the whole world. Thank you so much for joining me on this explainer today, and keep your curiosity focused.